Good afternoon, one and all.
Yeah, good afternoon.
Good afternoon, sir.
Yeah.
Good afternoon to everyone present here. I extend a hearty welcome to all of you to the keynote session 4 titled Influence of Phase Change Materials on Thermal Properties of Nanosilica Admixed Cementitious Materials by Dr. Bibhuti Bhushan Das. Sir, just before we begin,
Yeah.
a small introduction about Dr. Bibhuti Bhushan Das. Dr. Bibhuti Bhushan Das is currently working as an associate professor at the Department of Civil Engineering, National Institute of Technology, Karnataka, Suratkal. He obtained his BTech from Orissa University of Agriculture and Technology, MTech from Indian Institute of Technology, Delhi, in Construction Engineering and Management, and PhD from Indian Institute of Technology, Bombay. He also has a postdoctoral from Lawrence Technological University, Southfield, Michigan, USA. His major areas of interests include concrete technology, sustainable construction, building materials. He has been honored with fellow membership from Association of Consulting Civil Engineers, India. He also served as committee member, Indian Standard Code for Fabrics in Construction, Bureau of Indian Standards, New Delhi. He has published 41 papers in recognized journals, Scopus only, 49 book chapters, 17 conference proceedings in various fields. His research has attracted the attention of research community as evident from 930 citations and an H-index of 16 in Google Scholar. It is an honor to have you here, sir. I
Thank you
request
so much.
you
Thank
to
you.
go ahead with your technical keynote session. Thank you, sir.
Thank you. Thank you. Okay. So thank you so much for this nice introduction and thank you the organizing team for inviting me to deliver this keynote lecture. Uh, so I'm going to speak about a very like theme based topic here actually that is mostly towards the thermal efficiency. Okay. And that is nothing but the phase change materials. So I will speak about like how we have come across okay like this concept of uh, storing the heat energy into the concrete system. So my presentation will be okay like will go like this in this way actually. And so what is the genesis actually? The genesis is like you know the concrete or a cementitious system at this point of time we are looking is necessarily to be a high performing material and necessarily to be a sustainable material. So with this point of view, first okay we have optimized a, a nano silica blended cementitious composite that is you can say is a high performing material as well as a sustainable material actually. But in addition to that, we have realized there is a scope to go into the transforming the nanosilica admixed cementitious composite into a thermal efficient material. So that is what is the need of the hour. So particularly if you like have experienced last summer, that is 2023 April, May, June, okay, like even some of the North India still okay having that effect. We have really felt okay the temperature has gone up significantly actually. So what we have to do now? Well, all our building materials now we are completely dependent on the concrete, the cementitious composites. So the problem here is the concrete or the cementitious composite is a very okay poor performing with respect to the thermal efficiency. So that is the reason it is necessary now to go into the move into a material or development of material where we can store the thermal energy and make the blended okay material a thermal efficient material. So, well, I will go into this. Okay, many of the presentations, many of places I have spoken about. Okay, like what is the hydration process for the concrete. So I will skip. Okay, because time is very short. So I will speak because many of the places I have spoken about what is hydration and how. Okay, like a bulk concrete. Now in this slide you can see the bulk concrete, which is in 10 to the power minus 0. That is a meter scale specimen. That is, we are anticipating the performance in this kind of size specimens, whether it is a beam or a column or a foundation or a slab, whatever it is. But the chemistry lies into the complete to the left side. That is the CSS colloids, the gel networks, the molecules. Okay, so that is the chemistry, and that defines the performance of the bulk concrete. So, well, I will skip. Okay, like where we have spoken about the molecular dynamics. So, so this is what is nothing but okay, like a development of a nano engineered concrete. So where like uh, it is necessary, okay, to go ahead with the addition of the nanoparticles. So, so what is this slide actually with respect to the size, with respect to the particle size of the material? The moment you keep on adding the smaller to smaller sizes, you can able to produce the conventional concrete and then high strength or high performance concrete and then the nano engineered concrete. Okay. So what is a nano engineered concrete? Well, it is nothing but a nano ingredients with at least one dimension of nanometer in size. So that is okay. The nano science or you can say the nano engineered concrete with respect to the concrete science. So there are a lot of advantages. Okay, like so what is the hydration particularly mechanism says when you add cement, when you add nanoparticles into the cement and water, the formation of orthosilicates that gives me a kind of additional calcium silicate hydrate. So, and how it gives me? Well, it nothing but act like a seeds and the formation of the more compacted calcium silicate hydrate phase, and that is what is being given by the other nanoparticles. In addition to that, nanoparticle also is a highly pozzolanic material. So because of the highly pozzolanicity or the system, we get extra calcium silicate hydrates. And that is the way we get a very much compact and dense hydrated products. And that gives me a long lasting, a long lasting material, okay, or you can say the a durable material. So this also I will just go skip actually. This is all of the molecular dynamics. Okay, but what is the challenge actually here? The challenge is the when you deal with a nanoscale particle size material, okay, nanoscale material, it what happens actually? It accelerates the hydration rates and reduces the workability. So smaller particles as nanosilica also produces the shrinkage, that is large number of microcracks, and accelerated heat of hydration is governed by the curing. So means you have to have a very good quality control practices. That is necessary when you deal with a smaller to smaller size particles. Otherwise, it is going to give you a problem. So you can see that is what is happening actually. So the moment you lose water, so there is nothing chance except the formation of the shrinkage cracks. So India is a very tropical country. Now you can so you have like we have very challenging like climatic conditions. So as per the Indian code of practice, we have 5 kind of climatic zones. That is hot and dry, warm and humid, composite, moderate, and the cold. So 5 climatic conditions, and the variation of the temperature is quite a large. It's quite a large actually. So in the south particularly, when okay, now we are having a intense rain, if you go to the north, still okay, the rain has to start. So we have a variety of climates among across the state, across the country actually. Now, what is the challenges? The challenge is the summer and the winter. The variation in summer and winter for particular okay class few climates, the variation is too much. Like you can see the hot and dry climates. Like summer, temperature goes up to 45, 46. Okay, sometimes it is 50 degrees centigrade, and winter temperature comes down to even 0 degree at the night. So that is the variation, okay, from summer to the winter. So we have done okay some kind of life cycle, okay, like energy distribution over the design life of a building envelope. So many okay like variety of like envelopes we have considered. We realized the operational energy is the largest okay consumption of the energy okay in the service life, in the life cycle of the building. So you are almost spending okay like 90 to 95% of the energy okay in its life cycle. That is nothing but your operational energy actually. So what is the need actually at this point of time? Well, the need is you have to like have a energy efficiency of the energy efficient material. That is it possible okay to by any means we can increase the energy efficiency of the materials so that the thermal load okay can be cut down. So that is the best way okay to conserve the energy actually. So how it is possible? Well, possible is there is a method okay like by integrating inexpensive latent heat storage material into the building materials. And at this point of time, that latent heat storage material known as phase change materials are gaining a lot of attention owing to its thermal efficiency. So means you have to work or integrate the phase change materials, that is nothing but your latent heat storage materials, into the building materials. And that is the way you can make okay the system more efficient in conserving the energy. So what is the like basically okay the my phase change materials? My phase change material is nothing okay that but materials with an ability to absorb and release heat when the material changes from one phase to another, that is solid to liquid phase, liquid to gas, and vice versa. So what is the my working principle? Now see the left like circle, like PCM okay like PCM in the solid state, and when the temperature rises, so the heat that is uh, that produces because of the rise in temperature getting absorbed by the phase change materials, and it gets melted. So you get the PCMs in the liquid state, and at the same time when the temperature falls, so this heat it is getting released, and while the in the process my phase change material is getting solidified. So this is the working principle of the phase change material. So with respect to if you want to see the with respect to the energy absorbed okay or released, it is nothing but okay like this plot right side, come to the right side plot, that is the my temperature in the y-axis and energy absorbed or released in the x-axis. So you have the material, the moment okay your temperature increases, okay temperature increases, so at this particular stage okay at this okay solid line, the left solid line okay when temperature increases, so your solid is getting converted into the liquids, okay. And a particular okay temperature when falls down, that is this liquid okay, this solid okay this solid is uh, is again okay getting into the liquid. Means, so means this in this boundary okay, like I'm saying is the isothermal condition where the phase transition is going to happen. So means the at that particular temperature zone, my material is getting converted okay into the solid to liquid and liquid to solid. So what happens actually, like when you integrate the phase change material in concrete particularly, so what happen what it does actually in hot day time, PCM absorbs surplus heat by getting melted, and that is the way it minimizes the load of air conditioning. You know the principle of the heat absorbance is a liquid okay, like particularly it takes a lot of time to get heated actually. Okay, so what happens the moment the PCM absorbs the heat, it will convert into the liquid form, and thereby it will not allow the heat inside the building. So it is going to absorb all the heating load, and that is the way your air conditioning load is going to be minimized. Similarly, in the in the cold day time, or you can say, for example, like in the night, okay, if there is a the diurnal variation is too much, then you can say the night, okay, like the PCM becomes solid and the stored heat is released back. So means in a cold day time, you no need to switch on the heater. You no need to switch on the heater because it will not allow the the cooling okay, the outside the cooling okay into the building, because this is going to be solidified. So that is the way it will minimize the load of heating. So what happens actually, hence the PCM concrete minimizes the temperature flux of outdoor weather condition and is capable of stabilizing the indoor temperature of building under the constraints of transition temperature of the PCM you chosen. In addition, we have realized it also benefits in eliminating the micro cracks and volume changes that arise due to thermal stresses in massive concrete structures. Well, we have not okay worked on the massive concrete structures, but we have checked the shrinkage properties, and yes, it eliminates a significant amount of the shrinkage. So what happens actually so well? So, but this okay, like picture says, like even though outside okay the variation is too much okay with the time okay but too much, but inside if you have a PCM integrated wall okay, or you can say thermally insulated wall, you can maintain your room temperature a uniform okay, temperature you can maintain inside your building actually. So what is actually at this point of time now, what we realize actually, PCM, that is presence of PCM in cementitious composite suppresses the hydration process, increases the loss in mechanical strength and porosity, which hindered its practical applicability in cementitious products. So the challenge here is the moment you add patch and material, your hydration is going to be hindered. So if your hydration doesn't happen, what happens? Well, definitely okay, there will be loss in compressive strength and increase in the porosity. So that is what is we don't want. So that is the reason what we have done actually. We have integrated okay the cementitious the phase change materials into the nano silica based cementitious composites, and we have used PCM as a latent heat storage material, and that is the way it it means we say the nanoparticles which which normally okay gives a high heat of hydration and also the shrinkages and associated thermal cracks, but a PCM based material is just reverse, means hydration is slow means it's like low heat of hydration. It's just opposite actually, and it minimizes shrinkage and also the thermal cracks. So if you add both, they will okay balance each other's deficiency, and we can take the both of their advantages. So means if you the drawbacks of nanosilica based cementitious composite can be mitigated by the drawbacks of PCM based cementitious composites. So thus you can produce a thermal efficient, sustainable and high performing construction material. So methodology, I will go quickly. Like these are the materials um, like OPC, fine aggregate, then physical properties of the colloidal nanosilica, then physical properties of the PCMs that we have tried. Okay, in the study, we have tried three. Okay, like PCMs, that is paraffin wax waste, and octadecan waste, and then sodium okay carbonate. So you can see paraffin was in solid form, octadecan was in liquid form, and sodium carbonate in powder form. So this is the way, okay, like we've used the cemented system, and you can see here the nanoparticles. You have used a 20 nanometer size particles and in a colloidal form, just to avoid any kind of safety okay hazards. So this is the particle size of the OPC, sand, and nanosilica. You can see the so my OPC stands in the micrometer zone. Okay, my sand okay lies in the millimeter zone, and nanoparticles lies in the nanometer zone. So these are the mixed proportions where control, then OPC plus N octadecan 1%, 3%, 5%, sodium carbonate 1%, 3%, 5%, then OPC 1 plus paraffin 1%, 3%, 5%. So we tried okay different proportions, and similarly the next stage okay what we have done actually OPC plus nanosilica 3%, then OPC plus N octadecan 1%, then OPC. Uh, so what we've done actually, what I've done, I will tell you. We have taken all these initial mixes, and from this we have chosen only the best performing mixes. Means first we checked with kind of okay, like uh, phase change material doesn't okay hinder too much of hydration process. So if it hinders too much, then it is not good for me. So means out of all these three, you can see N-octadecan, sodium carbonate, and paraffin, we have realized only the N-octadecan is performing the best. Means for my requirement, N-octadecan is only okay working with my material. So in the second stage, I have reduced okay my mixes to only N octadecan. So so OPC plus N octadecan 1%, OPC plus N octadecan 3%, OPC plus 5%, which I have already done actually. So in here, what I've done actually for all these three mixes, I have added 3% of nanosilica, and that was okay. Like the one of our studies, we have realized 3% nanosilica is giving the optimum okay mix actually. So all the specimens okay were like mixed and cast to standard okay like testing methods, same okay like cubical specimens, then cylindrical specimens for the RCPT test, then prism specimens for the drying sinkers. Okay. And these are the standards okay like compressive strength, drying sinkage, and RCPT. Through by following these standards, the test okay were made actually. So these are the specimens. You can see the mortar mixer, then the specimens, and all these okay like all kind of testing okay methods presented here. So I will just skip okay this actually. So what we did actually, we have done okay two types of mix. One is for a mortar, that is for the all kind of okay compressive strength test, then shrinkage test, and then RCPT test. But for advanced characteristic studies, like to check okay the my hydration phenomena, to check okay the mineralogical phenomena, to check the thermal okay, that is differential scanning calorimetry test. We have taken the paste specimens, same proportion, but we have done for the paste. So for a paste, you can see right side, okay, you can see this is silicon mold normally being used for chocolate preparing chocolates. So we have prepared small size specimens that is diameter 2.1, lower die 1.9, and height is 2. So these are the like sizes. Okay, like we have casted okay small specimens, and we have followed all the standard okay procedures of the casting, and then after certain okay days, that is 7 days, 28 days, they were okay subjected to advanced characterization studies. Okay, that is pozzolanic reactivity test, but I will skip this one. Okay, it is already published. XRD, TGA, and DSC. I will speak more about today TGA and DSC, mostly DSC actually, because this talk is towards the thermal efficiency. Okay. Also, we have done the SEM EDX analysis. All right. So this is the way like paste. Okay, were characterized. So first we characterize the paste, and then okay we did the advanced characterization. So as I was talking about the how we have realized it is stopping the hydration. Well, that is through the thermogravimetric analysis, that is TGA. If you do a TGA of a cementitious composite, you can understand how okay my hydration phenomena happens. How? As you know, we have two compounds, that is calcium silicate hydrates and calcium hydroxide. So if you can measure or determine the CH, that is calcium hydroxide, and the double H, that is nothing but my CSH actually. So you can able to tell yes how my hydration phenomena is happening. Okay. Similarly, XRD okay like was done okay through X-ray diffractometer, then scanning electron microscopy and energy dispersive X-ray spectroscopy also was carried out. Then the measure okay important okay for this talk, today's talk, is the differential scanning calorimeter. I will speak about more about this. So we have taken the specimens and did okay a differential scanning calorimetry to understand how much energy it can store. That is okay, means how much heat energy okay my material can store. That is very important actually. So thermomechanical performance of Nano Si2 and or PCM based cementitious mortar. So this is my compressive strength. Okay, I have spoken about okay in many of the presentations. Okay, you can see okay like some of the recordings in the YouTube or maybe some of the papers. Okay, so I will skip this. The moment you add nanoparticles, well, I am getting a tremendous increase in the compressive strength, and that too at the age of 3 days itself. So that is the my advantage of adding a very small percentage of nanoparticles. So what we have done actually, when we have gone with the phase change material admixed material into the cementitious composite, we have realized I have to go ahead with a phase change material which gives me at least 35 okay MPa compressive strength. Otherwise, I cannot go forward actually. So 35 MPa was chosen as a benchmark. So 35 MPa. So I have realized the except okay, N octadecan, all other materials, sodium carbonate and paraffin, failed to achieve 35 megapascal. So further studies I have performed only with octadecan, nano octadecan, N octadecan, okay, material actually. Okay, so these are my integration of nanoparticles and how okay with time I'm getting the compressive strength. I will skip this one actually, okay. And this is nothing but your the shrinkage I was talking about. The moment you have using a PCM admixed mortar, your shrinkage reduces substantially. Okay, that is the advantage when I'm using a, a PCM admixed cementitious mortar. Now you can see the the red one, okay, that is CNS, the it is giving me the maximum, okay, strain actually, because that is having 3% of nanosilica. And I was telling you, the moment you add nanoparticles, that is going to give me the maximum shrinkage. Okay. Similarly, like you can see this, the green one, okay, nothing but is the 5% of n octadecane, and that is giving me the lowest shrinkage. So because I am adding phase change material, and that is going to that is going to absorb the heat, okay, within the cement system that is available. So similarly, RCPT, okay, like anyway, this slide not much important at this point. Setting time, surface temperature, chemical sinkage, okay, like yes. Now this is very important for me. Now what we have done actually, we have taken the cementitious, okay, mixes, and we have done the differential scanning calorimetry. So what you can see here? Well, this black line is nothing but my cement paste. So when I am going ahead with the temperature, you can see it is going a black line actually. Okay, there is no heat is getting stored, because as I was telling you, a OPC, a normal concrete is very poor, okay, in heat absorbance. Okay, heat absorbance. So that's why they are conducting the heat. But here now let us go into the n octadecane 1%, and this is 3%, and this is 5%. The means the moment I am increasing the dosage of PCM, so heat capacity means heat absorbance capacity is increasing. Okay, and what is happening actually, onset and temperature of DSC curve for the octadecane mixes were started from 13 plus or minus 2 to 27 plus or minus 2, and the peak temperature is 18.2 plus or minus 2. Means you can see this is my peak temperature, and this point the solid, or you can say the transition, the phase transition. So and octadecane will change its phase, or you can say the phase change material will change its phase. But how? By absorbing the heat, and that's what it is visible here. You can see this okay, like peak, this peak nothing but okay is my the signature of the heat absorbance. So how I will do? Well, you can measure the enthalpy of change in phase, that is measured as area on the DSC curve. So this is my starting temperature. This is my end temperature where I'm getting a major peak. Means that is the point where my heat is getting absorbed. So you can measure the enthalpy. That is, if you can do the area or measure the area, and it is nothing but there are so many softwares are available which will give you the area. Okay, if you upload these curves. Okay, so that is what is my uh, only okay PCM based material. Now second one you can see now. The black one is the control motor. It is just a straight line, and the colored nanosilica 3% when I added, it is also just a black line. There is no much okay change in okay the in the peaks, or means there is no okay capacity okay of the heat absorbance. So now you can see this red one is nothing but your CNS 3% plus octadecane okay 5%. Okay, octadecane is 5%. Means it is giving me a peak, and it is absorbing the heat. Now what is the blue one? Blue one is only octadecane. So means the octadecane, like what are the temperature boundary for octadecane? Well, it just okay like the 18 plus or minus 0.2 degree. So that when I'm adding okay nanoparticles and octadecane, that is phase change material, So there is a shift in peak temperature. So that is 20.3 plus or minus 2. So means, well, there is a small reduction in the heat capacity, but yes, I'm getting a peak. And I am able to absorb a substantial amount of heat, or substantial amount of heat can be stored. So what have we realized? Well, if you are going ahead with only PCM, also fine. You can absorb sufficient amount of heat. But if you want to make your material a high performing material, that is nanoparticles plus PCM, also you can able to absorb the heat. But we have realized latent heat we have was observed to be reduced, okay, by 25 to 50 percentage. So it is fine. So means the nanoparticles, when I'm adding, the heat absorbance is reducing, but it is not reducing to zero. It is able to, okay, absorb a substantial amount of heat. So you have to choose. You need whether it is a just a like PCM based material, or maybe a means that is giving me a very low strength, or maybe a nanoparticle admixed PCM based material that is going to give me a sufficient amount of strength, compressive strength, that we normally go mad about, okay, like civil engineers, we go mad about compressive strength, and as well as the latent storage capacity. Okay. So this is nothing but, okay, like it is same thing what I told you. So basically, like I am going ahead, okay, with, okay, this is my CNS, okay, like 3% plus 1% silica. This is 3%, 5%. You can see if you compare both the things here, okay, the my peak was very sharp, but the moment I am adding nanoparticles, the my peak is getting little flattened actually. Okay, peak is getting flattened, and that is what is I will say little bit, okay, a amount of heat storage of the capacity is I'm losing by adding by going with the nanoparticles, but simultaneously I'm making the material a more, okay, more stronger actually, more more highly performing. So next is the TGA. So I will just quickly go ahead. That is, so you can see this is not my TGA, this is my DTG, that is derivative thermogravmetric curve. And if you do the DTG, then only you can get this kind of peaks. All right. So normally in a normal, like if you see some of our papers in a normal concrete, but whatever is here also it is there. Now there will be a one peak, that is calcium silicate hydrate, and there is a second peak, that is calcium hydroxide, and third is my calcium carbonate. So there is normally you get three peaks. But when you add PCM, now you can see how, okay, the dotted line, okay, say it is performing. One is my CSS, and this boundary of temperature, that is 200 to 300 degrees centigrade, I'm getting one additional peak actually, additional peak. And my CS almost similar temperature, even the CC also similar temperature. So what happens, what we realized, well, nothing but, okay, this peak is getting small, means the hydration in the initial days is slowed down, and it is pronouncing, okay, in one additional temperature range. And that is nothing but, okay, you can say is a thermal degradation curves for the PCMs. That is between 210 to 300 degree centigrade. So we have, okay, like you can see some of our papers. It is this work is published already. Okay, so this is all about like the integration of PCMs into the cementitious system. So this TGA is nothing but, okay, like is very much, okay. I spoke many of the conferences, so you can like even so many papers it is also there. So this I will like skip actually. And well, this is, okay, your extra diffraction. So what it gives me, like you can see, like um, like colloidal nanosilica plus octadecane mix, that is giving me a strengthened tobermonites and the reduced peak of calcium hydroxide. So if you see the only n-octadecan mix, well, we have a sufficient amount of calcium hydroxide. So that is the difference actually. In addition to like the all other things are almost similar here. And if you go into the SCM with EDX, that is where I can able to understand the morphological characteristics of the cementitious system. Well, what we have done actually, we have gone into the elemental composition analysis, that is atomic percentage analysis. And if you see the Ca by Si ratio, my all my PCM based material, that is octadecan 135, you can see my like Ca by Si is quite a large. Okay. Whereas the moment I'm adding nanoparticles, this is reducing down, means the formation of the hydration products are getting better actually. So I can say it is always a go ahead with the combination of the phase change material in addition to a nanoparticle kind of materials. So, well, I am into the conclusion actually. So the compressive strength is fine. Like, so I would say like with respect to the thermal efficiency, the moment I am going ahead with the addition of phase change material into the nanoparticle admixed cementitious composite, what I am achieving actually, I am achieving a parameter called thermal efficiency. And that is at this point of time is need of the hour. We are now, the world, okay, is facing a global, okay, climate change. And every one of us now need air conditioners in the summer and heater, okay, in the winter. By adopting this kind of material, you can literally, okay, like avoid, okay, to a some extent. To say, I'm not saying is 100% you have to, okay, not required, S is not required. No, to some extent, your heating load, okay, is going to be reduced. Simultaneously, your cooling load also going to be reduced. So that way you can save an enormous amount of energy, and that is nothing but, okay, one of the objectives of this conference actually. So we have to understand the global sustainability. So by adopting this kind of material, we can literally, okay, achieve the sustainability. So by this, I am just, okay, say, okay, like these are the published, okay, work, okay, particularly on this particular theme. So many, okay, like papers are there, okay, so many like places we have published extensively. We have published on the phase change materials, then combination of phase change materials and nanoparticles, and you can follow it, you can go through it, and any point of time if you need, okay, to discuss, well, you can call me or you can simply, okay, write a mail, and I will be happy to, okay, answer your queries. So thank you so much. So by this, so I am just, okay, like um, allowing the audience, okay, like you can ask few questions if you guys, okay, really want to have a discussion. Okay,
Thank you. Thank you, sir.
thank you
Uh,
so much. Yeah.
I'll be allowing the participants to unmute themselves. If anybody has any question, please go ahead. Any questions, please? Sir, actually, I only
Yeah,
wanted to know,
please.
so you discussed about SEM and other advanced characteristics of phase change material,
Yeah,
but
yeah,
what about the, when we were speaking about the thermal efficiency and all. So
yeah.
could you please discuss a little more about crack formations in these composites, sir?
Okay. No, what happens actually, I will tell you what happens. Uh, the moment you are, see, at this point of time, like we are now moving towards high performance. Isn't one of the criteria, okay, like of going ahead with material is high performance. Means what is high performance? Well, I need high strength as well as it has to last long, isn't it?
True. Yes.
So that is what, okay, is our objective actually.
Mainly.
But
Yes.
but what happens? So means if you want high performance, for development of a high performance material, you need a smaller size particles. Like we were using, okay, the flyers, GGBS, but nowadays we are using the ultra fine flyers, even ultra fine GGBS. And now at this point of time, we are moving towards nanoparticles. Okay, even much smaller size actually. So when you are moving towards smaller size particles, the biggest challenge is the shrinkage.
Linkage. True.
So what is the what is the like problem of our construction sector? Well, we develop a material in the lab and we say, yes, this is my compressive strength and this material is very good in the RCPT test, everything is fine. But when you take it to the field, the biggest challenge in India is we don't, okay, practice the good quality control. Means they don't care about the curing. You know, okay, like you must have seen, okay, the road construction must have going on in Bangalore, okay, and here also in Bangalore. Nobody is, okay, okay, like so so these are the one of the conditions of the
Field.
strict quality control. Yes, quality control practices. Okay, so means if you avoid, okay, like the curing, definitely, like, you will have sufficient formation of micro cracks. Okay, and that micro cracks will lead to later point of time will go for a durability issues. So means your material that you have designed, okay, for 50 years or maybe 100 years will last only 20 years, 25 years. So this is what is the problem actually. So what we are doing actually, what we have realized. So the moment we are adding nanoparticles, even though it's a very small percentage, some of our research we have added only 2% nanoparticles, and we have got a very good performance. But the problem is in the field, nobody will adopt a strict quality control. Okay, so what we can do actually, we have to like mix 2 3 materials. Like one material is this material actually, phase change material. Well, one of the requirement for us was to develop a thermal efficient material, and we have realized like if we add PCM, phase change materials, we can able to develop a thermal efficient material. But the problem is there is a deficiency in the hydration process, because they are blocking the hydration process. They are not allowing the hydration to happen. So thereby your compressive strength is reducing down. Okay. So,
Yes.
but I need compressive strength as a civil engineer. Okay, I need compressive strength, isn't it? Everybody wants
The
compressive strength.
priority.
Priority, yes. Okay, priority. That is the only means point. Okay, where code allows. Okay, like so means we realize, okay, we have to add a very high performing material. So we have realized, okay, yes, this material can be clubbed with the nanoparticles, and that is the way I will get my high performing. That is my compressive strength what I require. Suppose I here I've gone up to 50 megapascal achieving by this combination. In addition to that, I can able to like develop a material which can absorb a sufficient amount of heat within the system, and that way I can reduce the energy loads.
Okay. Okay, sir.
I think I have answered your question, or still you?
No, sir, you have actually, but yeah, that is true that the quality control issues are persistent in our
Yeah.
industry right now.
So specific, we have specific papers, like the publications are there. I think I will show you like some specific, okay, actually publications are there. um I will send you, okay, like, because these are, I think here we have not much studied about the shrinkage, but when we have developed a specific nanoparticle based materials, we have studied extensive, okay, research on the shrinkage part actually. And it
Okay.
is published also. It's very good journals, okay, it is published. So I can send you, okay, like how to characterize, okay, this shrinkage, and then work on forward actually.
Sure, sir. Please, sir. Thank you.
Yeah, yeah.
Anybody else? I would like to ask any question.
Sir, good afternoon.
Yeah.
So actually, likewise, the topic is very nice as you were discussing about the thermal behavior of the nanoparticles used as a composite material in the
Yes.
construction.
Yes.
Yes, sir.
Yes. Yes.
So the thing is, can we get some benchmark thermal conductivity of the material as to what will be the range?
Yeah.
Yes.
So see, actually, like you have see, I didn't speak particularly about this thermal conductivity range. Okay.
Yeah, definitely. But you
Why?
spoke about the heat storage.
Yes.
Like,
Yes.
yeah,
Absolutely.
yes, sir. Yes,
so
sir.
so actually we have measured the thermal conductivity, but I didn't speak okay about in this presentation
Yes, sir.
because okay, like you have now I spoke okay, like I spoke about a genesis, like
Mm-hmm.
how to develop a thermal storage material. Okay.
Mm-hmm. Yes, sir.
So so you have several options. One is like you can like you can adopt okay, variety of phase change materials. Okay, that
Mm-hmm.
is available in the market. Okay,
Mm-hmm.
and depending on your requirements, like you need okay more energy to be stored in your system. Okay, or in your application. But the compressive strength you can compromise. You don't need much okay about the compressive strength. So accordingly you design it. Okay, you design okay depending on your requirements of thermal conductivity. So I have chosen, but particularly for me, I have chosen okay, no, my benchmark has to be 35 megapascal.
Right, sir.
Okay, then only I mean because most of one such industry told no sir, we it has to, I cannot okay like sell the material. So then I told okay fine, okay let me make it 35 and see how much I can make the thermal conductive. All right.
Yes, sir. Right,
So
sir.
so that's why I didn't speak particularly about thermal conductivity.
So that means we still need to do the research on this particular aspect.
No,
Yeah.
no. I'm telling you, I'm not speaking about it. Okay,
Okay.
because
Right, sir.
we have
Right, sir.
already
Yeah.
done it. Okay, all
Yeah,
right.
right, sir. Right, sir. Actually, the thing is
Yeah, yeah,
to put it in a code for the ECBC, we still
yeah,
have to
yeah.
benchmark the values. So then only we, as you have told, that the quality assurance while using on the construction as well as, first of all, actually, it should be acceptable in the market, right?
Yes, yes,
Yes,
yes, yes.
right, sir. Yes, sir.
No, your question is it is a very good question actually. It's a very good point actually. We have to specify a material okay when it goes to the market with respect to its thermal conductivity. I agree.
definitely. Yes,
Okay,
sir.
I agree. Okay, that's why I was speaking about. I told okay, yes, thermal conductivity is very low. Okay, for a concrete means
Yes, sir.
thermal absorbance is very low. Thermal conductivity is more.
Mm-hmm.
So
Right,
we
sir.
have to speak okay like about thermal conductivity, but I
Hmm.
didn't give you the value because I
Yes,
told you
sir.
this is for a company. Okay, all right.
Right, sir. Right, sir. Thank you so much,
Okay.
sir. Thank you so much, sir.
Okay.
Thank
Thank you
you.
so much. Thank you. Yeah.
Thank
Yeah.
you.
Right.
Thank you.
Right.
Good day, sir.
Thank you, sir. Um,
Yeah. Thank you so much. Yeah.
Yes, sir. We are humbled by how well you actually responded and gave your no keynote, sir. Thank you so much for being a part of IACESD 2023. Thank you for taking your time out of your schedule, sir. We are sure that most of them have found the session to be more valuable and informative. So if there are any other questions regarding the topic, I'm sure we can ask this through the YouTube video session, which will also be shared. Sir, once again, thank you so much for taking time off, sir. We are very grateful for your time, sir. Thank you. Thank you so much.
It is my pleasure. Actually, I could have been there, but I could not. Okay. Because,
Yes,
so
sir. We
there
actually
are some
expected you here.
yeah
Yes.
there are some restrictions. I have a small kid actually, so I cannot okay like leave okay them here. Okay.
We understand, sir.
So just convey my regards to Dr. Like SreeKeshava. Like he was very much okay like communicating okay like through email.
Yes, yes, sir.
And maybe sometime, okay, like again, okay, like given a
Please,
chance.
sir, you're always
Okay.
welcome to
Yeah,
join.
yeah, right. Okay. And thank you so much, one and all.
Thank you. Thank you.
Yeah,
Thank you
yeah,
so
yeah.
much.
Thank you. Thank you.